13.4, we're going to be dealing with mutually exclusive and independent events. So now we're going to be working with numbers a bit more. But we got to figure out we need the definitions for mutually exclusive events and independent events. So mutually exclusive events, these are two events are mutually exclusive if they cannot happen at the same time. The probability of the two happening at the same time is 0. Okay, and when it comes to mutually exclusive events, we can figure out the probability of A or B of the two events by adding up the probability of A plus the probability of B. Okay, moving that up a little bit. Two events are independent if the occurrence of the first event does not, it's T, affect the probability of the second event. So the probability of A and B is going to be the same thing as the probability of A times the probability of B. Sorry, it's a little squished. I'll rewrite that down here. So the probability of A and B is the probability of A times the probability of B. So like we saw with the flipping the coins, right? Those are independent events because when I flip a coin once and get some result like heads, let's say, and then I flip it again, the fact that I flipped heads the first time doesn't change the probability of my flipping heads the second time. There's no effect between the two. There's no change that occurs in the probability. So then my probability of flipping heads twice, let's say, is just 1/2 times 1/2. So the probability of flipping heads and heads, let's say, is just the probability of flipping heads times the probability of flipping heads. So it'd be 1/4 overall. Okay, there's another formula that we use for independent events for the probability of A or B. And that's the probability of A plus the probability of B minus the probability of A and B. All right, so knowing these three things, this formula, probability of A or B for mutually exclusive events, and the probability of A or B for independent events, and the fact that probability of A and B is the same as the probability of A times the probability of B, that's going to be important. So I think it's pretty helpful, especially when it comes to these formulas, to give you maybe a glimpse of what motivates them. So like, why are we writing it like this? Why are they structured like this? One of the ways to think of mutually exclusive events and independent events, you don't have to write this down if you don't want to, but it might be helpful. If not, then I apologize. So if you think of mutually exclusive events, they cannot happen at the same time. So let's think of this in terms of diagrams, Venn diagrams. So we can have something that looks like that, and we can have something that looks like this, let's say. And let's say that this is A, and this is B, and that's A, and that's B. Okay, so for mutually exclusive events, they can't happen at the same time. So there's no overlap. So these would be mutually exclusive. So then if we're looking for the probability of A or B, we don't really care about overlap, probability of A and B happening at the same time. That's just 0 for mutually exclusive events. A and B, probability of A and B for mutually exclusive events is just 0. But we look for probability of A or B, so either one of these happening. It's just going to be a matter of adding up the probability of this first one plus the probability of the second one, straight up, because they're separate and there's no overlap. Now, if you want to figure out the probability of A or B in this case, where these are independent events, and independent events can happen at the same time. They don't have to happen apart from each other. In the case of probability of independent events, if I want to figure out the probability of A or B, so probability of A happening or B happening, but not both, so or excludes the both part, then I'm going to be looking for the probability of A here, all this, let's say, and the probability of B here, but I don't want this middle part. I want to exclude that. So if you want to think about it visually, all I'm doing with this formula is saying the probability of A plus the probability of B. Now these two together would include this overlap. It would be this whole thing. But I don't want all that because I want to get rid of the both part, the and part. So I'm going to go minus P and B, which is just subtracting this section from the whole. So if you want to think about it visually, that's what's motivating this particular formula here, is getting rid of this overlap here, the both part, the and part. So
does that overlap would have been counted twice?
Yes.
Counted the probability of A and the probability of B. So you have to subtract the outcomes.
Exactly, yeah. So that's a little, maybe that was helpful, maybe not, but I thought it should be said anyway. Great. So let's move on to some examples. we have mutually exclusive events A and B. So disregard everything in the independent events category. We're going to be using mutually exclusive events, and we're going to be using this formula here. Okay, so mutually exclusive events A and B. Probability of A is 0.6. Probability of B is 0.25. So we want to figure out the probability of A or B. So nice, we have a formula for that. Probability of A or B is just the probability of A plus the probability of B. So this is just probability of A plus probability of B. And we're given values for that. Probability of A is 0.6. Probability of B, 0.25, exactly, 0.85. Right, so just a matter of knowing the formula and plugging in with our given values. Okay, now we're asked in 2 to figure out the probability of not A or B. Now this is something that we covered on Friday a little bit, but we didn't go that much into, and that's the complement. So the complement probability of something. One way to think of that, if you want to think of it visually, might be in terms of a loading bar. So let's say you have a vertical loading bar like this, and 100% is at the top, 0% is at the bottom. And in this case, we have 0.85, so let's say it's at 85%, where this is like 85% probability. If you want to figure out, this is the probability, all this filled in part, this is the probability of A or B happening. So then we have to figure out what the probability of A or B not happening is. That's going to be whatever's left over here. And remember that the complement of something, when it's added to the probability of something, so A or B plus not A or B, the probability of those two, that's just going to be 1. It's going to equal 100%. So remember, you'll never have probabilities that go over 1. That's just impossible. You never have probabilities that go below 0. It's always between 0 and 1 on some scale. Or in this case, between 0% and 100% if you convert it. So we know that the positive probability, the probability A or B is going to happen, is 0.85. What do you think the probability of not A or B happening is? Think what? 0.15. Yeah. Because what we're doing is we're looking at this bit right here. This is the probability of A or B not happening. Whatever is left over that needs to complete or add up to 100%. Right, exactly. It's out of 1. Okay. So when we calculate the complement, it's just going to be 1 minus the probability of A or B, which is we know is 0.85.
This is probably a silly question, but when it says probability and it says not A or B, the not goes to A and B.
Yeah, technically this isn't correctly notated because it should be, the not should be outside of parentheses with A or B in it, okay. But I think they're just not very careful with their notation. However, I should make one note because on your homework you'll have a different notation for not. So this is something, if you're nerdy like me, it comes from a type of algebra called Boolean algebra. But basically you'll have something like probability of this. So there'll be this little squiggly line in front of the A right here. This is called a tilde. It's in front of the A, or you'll have A or B and it'll be in front of that or whatever. That just means not. So remember that this little squiggly line in front of something just means not A. So it's the probability of not A happening as opposed to the probability of A happening. So I'm not sure, I haven't seen the test yet, but I'm not sure if they'll notate it with the word not or with the tilde or both, but I'll let you know. But just be wary that on your homework you have the little tilde there and it means not. Okay, so 3, the probability of A and B. Sort of a trick question. We should look back at our definition of mutually exclusive events. No. That's kind of like the probability of A or B happening, like them happening separately. The probability of A and B happening, so it's the probability of them happening at the same time. 0, right? Yeah, mutually exclusive events cannot happen at the same time. So A and B, the and, is that overlap. But there's no overlap between these events. think of the Venn diagrams. There's just two circles very separate on mutually exclusive events, no overlap. So the probability of A and B happening, at the same time, just 0. Okay, so now we have independent events C and D. So we're going to ignore the mutually exclusive events, and we're going to focus on independent events. And remember, independent events can happen at the same time. So if they ask us for the probability of C and D, we're going to have to answer. So actually, they already gave us the probability there, so 0.22. Okay, so for the probability of C or D, so we're given a formula for that. It's just probability of C plus the probability of D minus the probability of C and D. That's a D, not a 0, sorry. Poorly drawn. Okay, so it's just a matter of plugging in values. So probability of C is 0.55, probability of D is 0.4, probability of C and D, 0.22. Add up 0.55 and 0.4, get 0.95, subtract 0.22, and it's just 0.73. So once you've plugged in it for everything, it's just a matter of solving. It's usually fairly easy. Okay, now the probability of not C or D, or as they might write it, something like the probability of not C or D if they're using the tilde. Actually, they correctly notate it here. They, oh, not on yours actually, but they notate it correctly on the answer one. Interesting. So again, we're looking. This is the loading bar question, right? So we're looking for the leftover. What's left over to make 1 when you add the probability of C or D? So then we do what? How do we set this up? It's the complement. So we set up the complement by subtracting from what? From 1, yeah. So we're going to subtract from 1. It's going to be 1 minus the probability of C or D. Okay, we just found that out. 0.73. So let me just do 1 minus 0.73, and that's 0.27. Okay, so whenever you're asked probability of not something, remember you're just subtracting the positive probability of that, the probability of that thing, so probability of C or D in this case, or if it was not C, you subtract from 1 the probability of C, you just subtract that number from 1. So that's all you have to do there. Okay. Now we have independent events E and F, where the probability of E is 0.75 and the probability of F is 0.2. Okay, then we're asked what the probability of E and F is. They don't give that to us in this case. Well, remember, when they're independent events, the probability of A and B here is just the probability of A times the probability of B. So all we have to do is just multiply the probability of E times the probability of F. Plugging in, probability of E is 0.75, and the probability of F is 0.2. Multiplied together, you'll get 0.15. Okay, so with independent events, if you're given 2 events and you say, okay, what's the probability of E and F? It's just a matter of multiplying the probability of E and the probability of F together. Okay, number 7, the probability of E or F. Now we can use this big formula here. So we'll go the probability of E plus the probability of F minus the probability of E and F. Okay, probability of E is 0.75, probability of F is 0.2, probability of E and F, we just figured that out, 0.15. We'll add up 0.75 and 0.2, get 0.95 minus 0.15, Yep, 0.8. Okay, number 8. Again, it should have these parentheses here. It should be not E or F, not E or F. Right. So again, it's the complement. So how are we setting this up? I heard a 1. So we have 1. What's next? Minus, right? 1 minus. And what are we subtracting from 1? What's that? 0.8, right? Because we figured out not E or F. And we have the probability of E or F. It's just 0.8. So we're going to subtract 0.8 from 1. And all that is 0.2. Okay. So remember, again, complement. Know that. 1 minus whatever it is that is not that. Anyway, not that. That's confusing. Okay, so now we're going to identify some mutually exclusive events. Okay, so determine if the events are mutually exclusive. So flipping tails on a coin or drawing an ace from a deck of cards. One event, flipping tails on a coin. Another event, drawing an ace from a deck of cards. Are these mutually exclusive? Can these happen at the same time?
No. Well, I mean, technically, yeah, but it's very silly that we'll have a chance to get an ace.
Sure, yeah, but they can happen at the same time. I can flip a tails and I can draw an ace. So no, they are not mutually exclusive. So remember, mutually exclusive events, the only way to tell if something's mutually exclusive is to ask the question, can they happen at the same time? So whenever you're asked, determine if this is mutually exclusive, ask the question, can this happen at the same time? And if it can't, then you know, well, they can't. So it's not mutually exclusive.
It's like being in two places at the time.
Right, yeah, exactly. Can happen, right? Or rolling a 2 and a 6 with 1 dice on 1 roll. You know, that's can't happen. So 11, drawing an ace or a diamond from a deck of cards. Can these happen at the same time?
Yeah.
Right, you just draw it, ace diamonds. So no, you can draw an ace of diamonds. Hi, it's 4. I am, yeah. Uh-huh. Okay. Oh, yes, that is on the desk, yeah. Yes, we'll do. Okay, yes, sure thing. Yep, no worries. Sorry about that. Bye. Huh. Well, anyway, so 12. Choosing a freshman high school student or a junior student.
It's a mutually exclusive because you can't pick two things at once.
Right, exactly, yeah. So being a freshman or being a junior, I can't be a freshman and a junior at the same time. So, yes, mutually exclusive. And then you list your reason for that. So can't be both freshman and junior. Okay, so mutually exclusive events, we're asking the question, can these both happen at the same time? If they can't, then they're mutually exclusive. If they can, then they are not mutually exclusive. All right, so determine if the events are independent events. Justify your answer. So you flip a coin 2 times, or flip 2 coins, sorry, one at a time. The probability of flipping heads on the second coin after the first coin was flipped. Remember, independent probability, independent events, that's where the first event, when I do it, it doesn't affect the probability of the second event. So does flipping a coin and flipping another coin, does the first flipping of the coin...
It doesn't matter because they're 2 different coins.
Right, doesn't affect the flipping of the other coin. Even if it's the same coin, it wouldn't really affect it either. So
You can't pick heads and tails.
Sure. So yes, the outcome of the first flip does not or doesn't affect the outcome of the second. So you'll need to make sure that you write out, a little answer to why, or a little reason for why you chose that answer. Something just brief. Okay, number 14. So we're going to draw 2 cards with replacement. Draw a jack or a king. So with replacement means that, when I draw the first card, I look at it, I know what it is, and I put it back in the deck. So I'm not keeping it out of the deck. I'm replacing it back in the deck. So would these be independent events?
What does it mean by replacement?
Yeah, so I draw the first card out, I look at it, know what it is, put it back in. So I don't leave it out. So drawing 2 cards with replacement, does the first drawing of the card and replacing it back in, does that affect the probability of the second draw? No, right? Yeah, so yes, independent. Why is that? Well, because when I draw out the first card, my probability of drawing a jack or a king is 8 out of 52. But I drew a card out, but I put it back in. So this bottom number remains 52. So on the second time, it's also 8 out of 52. So there's no effect to the probability. Now, as you can guess, on the second one, draw 2 cards without replacement, draw a queen or an ace. Now, these are not independent events, so no. Why is that? Well, I'm not replacing the card. So when I draw it out on the first go, let's see, this is the first draw here, 1. I have an 8 out of 52 probability of drawing a queen or an ace. But on the second draw, because I left the card out, I now have an 8 out of 51 probability, assuming I haven't drawn a queen or an ace on the first go, of drawing a queen or an ace on the second go. So the probability has changed. So these are not independent events.
But if you had drawn a queen or ace on the first throw, it would have been 7 out of 51.
Right.
So regardless.
So either way, yeah, it would have changed. Okay, so remember, when evaluating mutually exclusive events, they cannot happen at the same time. So that's the question, can these happen at the same time? When evaluating if an event is an independent event, ask, when I do this the first time, does it affect the probability by doing it the second time? In the case of coin flips and dice rolls, probably not. In the case of drawing cards and not putting cards back in the deck, it does. Okay, so that is the notes. So you have the rest of the period now to